Hello everyone, we are gonna talk about our paper, Graph-Based Asynchronous Event Processing for Rapid Object Recognition. Rapid object recognition is essential for a variety of applications, such as autonomous driving and flying drones. For instance, when an autonomous vehicle is driving at high speed, the low latency is desirable to identify obstacles or moving objects once they appear. As a result, standard cameras are not suitable for this task due to their high latency. Standard cameras also have the disadvantages of motion blur and low dynamic range, which also hurt the performance. Different from the standard video camera, event cameras do not suffer from these defects, thus attracting more attention recently. As you can see in the short videos on the right, instead of capturing dense brightness images at a fixed rate, event cameras process the incoming light by measuring the brightness changes at each pixel independently. However, since the output of an event camera is a sparse asynchronous event stream, existing algorithms cannot be directly applied for event cameras. Researchers have developed different processing methods for event data, some of which apply current successful architecture after integrating events into the 2D image or encoding events into evenly spaced series. Some are also bio-inspired as event cameras do. Among them, graph-based methods have achieved superior results to the state-of-the-art while requiring less computation and memory, thus becoming an appealing solution. However, previous graph-based methods rely on integrating over a certain number of events. They gather the information contained in groups of events at the cost of discarding the low-latency nature of events data. A common follow-up question to ask is, can we unlock low-latency nature of event cameras while maintaining high accuracy at the same time? To this end, we propose a novel graph-based framework for event cameras. The core module is a novel incremental graph convolution which is based on sliding window strategy. The naive sliding window strategy, although ensure event-wise processing, is inefficient because it needs to process all the nodes in the graph even with a minor change. We thus propose a novel incremental graph convolution that exploits the local spatial connectivity of convolution and reuses previous calculations. For a single layer, it is rather simple to just compute the features around newly added nodes. For multiple layered GCN, we solve the propagation of modified features between layers with different graph topologies by deriving a series of propagation rules. We also propose an event-specific radius search algorithm for faster graph update with frequently events sliding in or out of the window. Our radius search algorithm is based on pixel queue, which is a commonly used event-specific data structure. It stores the most recent events at each location sorted by the time of their arrival. Our algorithm consists of two steps. The first step is to search in the image grid and filter out the candidate pixel queues that contain the events we want. In the second step, we traverse these candidate pixel queues. For target events in a candidate pixel queue, we compute their timestamps lower and upper bound, given query radius and spatial location. The index of the lower bound event and upper bound event can be located by binary search. Collecting events in all candidate pixel queues gives a final query result. A straightforward application of our event-wise processing framework is early object recognition. The insight is that the prediction result becomes stable when enough information is received, and it is not necessary to process more events. We fulfill this goal with the help of our state-aware module, that is, the top branch in part D of the figure. We verify our method's superiority on 4 datasets, including NCalTech 101, NCARS, CIFR 10 DVS, and MNIST DVS. Our method strikes a balance between event-specific low-latency methods and high-performance high-latency methods. On one hand, our method has the same low-level computational complexity as handcrafted and event-specific methods, for example, HATS, but our method achieves 15.6% higher accuracy on NCalTech 101 and 29.7% higher accuracy on CIFR 10 DVS. On the other hand, our method has less calculation than other second-best methods, for example, ASYNET. We also evaluate the efficiency of our pixel queue-based radius search with NanoAN, which is a popular KD tree implementation supporting dynamic update. Our algorithm is significantly better than the method based on KD tree when events frequently sliding in or out of the window. At the last, we show some qualitative results on NCalTech 101. It is worth noting our methods can recognize an object in foreground from events triggered by both foreground and complex background patterns. Here is the link of our project. You can also scan the left QR code to visit our project page. Thank you for listening.